This video will show you how to find the number of paths in a network. So in this example, there's someone named Alvin wanting to visit someone named Barbara across town. Alvin's just here, Barbara's here. Alvin also has another friend called Sally who lives just here in between. So the question's asking how many different possible pathways there are to go in between Alvin's place to get to Barbara's place. The first example in the question, we want no restrictions, so we'll look at that first. So you can see from here, we could move from A to B up the outside. We could move around the other edge. We could go up and across, up and across, up over here, or very slightly different. So you can see already there's quite a few different paths. Now in this question, we're not concerned with which is the shortest path. It's just how many different paths there are. All right, so we're going to use something called the number of paths algorithm. Each of these intersection points is a vertex, and the edges of this network are all the roads connecting these vertices. So first thing we do in the number of paths algorithm, just if you haven't heard the word algorithm before, it's just a sequence of steps that we follow, is we number each vertex with how many different paths there are to get to it. So this vertex just here, there is literally only one way to go from A to that vertex. This one here, there is also just one way of getting to that. Similarly, move over here. Now just remember we're moving in an upward direction, so we've got no interest in turning around and going backwards. So we assume that we're not going to go upwards. So I'll show you an example. We wouldn't go across, up, down, back, and return again. So we can just rule that out as an option. So because we're trying to work towards point B, we can say that there's also only one path to get to this vertex, because otherwise anything going from here, if we'd moved further up, we wouldn't be moving down to that point again. So we wouldn't move here, 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 and then back again. Similarly, there's one path to here, and only one path to get here or here. So that's quite simple. Where it gets slightly different is we could move up here to this point, or from here to here, and then up to here. So we say there are now two paths to get there. Now, because there's two paths here, at this point here, we've gone to two paths, so 1, 2, or we could move across to this point, then to this point, and up again. So now there's three paths here. Very similar on this side, there are three paths there. Once again, we could do any of the three paths to get to this point, or we could move along this path. So there's going to be 4 here and 5 here. So again, 4 paths to get here. All right, now because there's 3 paths to get to this vertex and 3 paths to get to this vertex, there are 6 paths to get to point S. There's 6 paths to get there, 4 paths to get here, so there's 10 to get to this point. You can see I'm sort of moving just slowly towards point B. If you just sort of went all the way across and up, you'd miss some out. So we just generally want to move in that A to B direction. So 6 paths to here, 4 paths to here, 10 to that point, and 15 to here, so 10 plus 5. And at this point, there are 20, and then 35 in total to get to B. So if there are no restrictions, there are 35 paths in this network. All right, so now we'll just change it a little. The question is now, what if you wanted to visit Sally just here? So if Alan wanted to visit Sally. So the first thing we can do for this question is we can rule out there are some vertices that we're just not going to go to. So there's no reason we could move from A up here across to there, but there is no reason we'd go to the top left and then back again, or to this point either. So we start by labeling them as 0, because there are no possible paths where we'd go there. Very similar, moving across from A up to S, we wouldn't go this far, because then we're definitely just wasting time. There's no way we'd get here, 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 or here. So now we've labeled them as zeros, we can just do the same path algorithm again. 1, 1, 1, 1, 2, 3. We're not going to go here anymore. 3 paths to here, 6 paths to get here. Then we've got 6 paths to get to here, which means there's also only 6 paths to get here because there's no way we'd go anywhere else. So that's 6. This is also 6. But now we've got potentially 12 paths to get up to here. Still 6 centimetres here, so that makes 18 paths in total. So if Alvin must visit Sally, there's 18 paths. There were no restrictions, there were 35. All right, let's try it again. Different scenario, now we're going to be pretty mean to Sally. Let's say Alvin must avoid Sally. So the first thing we do for this one is we say we cannot go here. That's the only location we can't go. So 1, 1, 1, 1 across here, just like the previous one. 2 paths here, 3, 4, 5. 3 paths to here, 4 paths to there. Now that we're not going past Sally, it does actually change this question quite a bit. So that's 4 to here. Now 4 straight up, 4 up to there, 5 up to here makes 9. 4 to this vertex, and 4 to this vertex means that there are 8. So it's still just simple addition, and that makes 17 to point B. All right, now the last part of this question is just having a bit of a think about it logically. Did we actually need to do that last part of the question? We knew there were 35 paths with no restrictions. There were 18 paths if you have to visit Sally. So if you need to avoid Sally, you could actually just take 18 off of that. 17. So the total number of paths, subtracting the paths with a certain requirement, actually gives the avoiding situation for that requirement. Okay, have a bit of practice.